everyone, and welcome to lesson 24.2. Today we are starting in your Springboard books on page 339, but some things you're also going to want to have up and ready to go are the reading guide that you should have kind of started with 24.1. You probably have a copy saved, so make sure you're opening that up to add to it. And then also your vocab handout that was also from the last lesson, because we have some stuff to add to that on slides 3 and 4. And then you'll also probably want a pencil and a calculator. Okay, so in today's lesson, we are talking all about theorems that involve chords in our circles. So we have in this first problem, they want us to draw in a diameter. So I'm going to draw that in. That's in black. Oops. And after we have our diameter, we also want to draw a chord that is perpendicular to our diameter. Okay, so here's our chord. So something that we notice when we have a chord and the perpendicular diameter is that the diameter is cutting that chord into two equal pieces, okay? So that's something that you're going to want to make note of down here with the conjecture, because what's happening, and this is we'll talk about the theorem later, but officially what happens is when a diameter, or a radius for that matter, when a diameter or a radius is perpendicular to a chord, then it bisects the chord. Okay, it cuts it in half. And again, an example of that picture is coming from up above on the page. Okay, so that's our first theorem about chords, is when we have a diameter or a radius perpendicular to it, it bisects the chord. Okay, so the next page then brings us our second example. Okay, so we see here a figure, right, in this circle, and what's being given to us in this is that our two chords are congruent. So we have AB congruent to DC. Okay. Now, when this happens, what we find out is that they are the same distance from the center of the circle, aka the word equidistant, right? It says they're the same distance. In other words, we're saying they are congruent to each other because that same distance or length is going to mean congruent. So equidistant kind of means congruent here. Okay, so what they're saying here is because AB and DC are congruent, we can now say that the center to the chord, so RY, that segment is congruent to RX. So that's our second theorem of the day. Now, to kind of pause before we talk about the last two theorems, we have some examples then that are kind of using that fact. So the first one is talking about number 6, and this is going to be on page 342. We're going to skip page 341 and jump here to page 342, number 6. And we have a circular clock that is has a chord that is 12 inches long. I'm going to draw on this chord. And it says that the midpoint on this chord is 8 inches from the center of our circle. So a lot of information happening here. So again, we are 8 inches from the chord's midpoint to the center of the circle, and the whole chord is 12 inches. So if we are cutting this in half with that midpoint, each piece is 6 and 6. Okay. Now, what we want to do from here is eventually calculate the radius of the circle. So think about the fact we can officially draw a radius anywhere we want on this circle. We can draw an infinite amount anywhere from the center to a point on the circle. But one place that's going to be really convenient for us to draw a radius is from the center to the end point of the chord on the circle, because now if we draw this in, we know this is a right angle because the chord is bisected. And we talked about on page 1 how that's a theorem. And now we can use the fact that we have a right triangle being made here to ultimately use our pal Pythagorean theorem to solve. Because right now we have 8, 6, and our hypotenuse is the radius. Okay? So our hypotenuse squared equals 6 squared plus 8 squared. 36 plus 64 is 100. And the square root of that then is going to be our final answer of 10. Okay, so we can use Pythagorean theorem to find that. Okay. Now, the next example, number 7, is nearly an identical example. We have a chord that's 15 inches long, and we know that that chord's midpoint is 9 inches from the center. So we're going to set it up the same way. This is 9. The whole chord is 15, so half and half would be 7.5. And we can draw in the radius to be found using Pythagorean theorem. Okay, so this time our hypotenuse squared is 7.5 squared plus 9 squared. So we have 7.5 squared plus 9 squared. And if we square root this value, we get 11.7 as our approximate length of our radius. Now, have to be careful though, because this one wants the diameter of the circle. So not just the radius from here to here, but we need to double that value to get the diameter, right? Because the 11.7 plus 11.7 would give us the entire diameter. So again, our diameter is going to be the 2 radii added together for a total of about 23.4 inches. Now, our next theorem is actually going to require us to investigate some things here. So we have intersecting chords. So notice we have a blue chord named AB and a red chord named CD. And what's happening is no matter what size we make these, however long our chords are, where they intersect the pieces AO and OB compared to CO and OD, if we multiply these two smaller values of the chord, they're going to always equal the multiplied values of the other chord, right? So we see, again, if we start moving this around, that AO times BO, the small times small of the blue chord, equals small times small of the red chord, no matter where we move these to be, okay, because this intersection. So if we go back to our notes to write that down, if you kind of draw yourself a picture, if we have our own version here of a chord named AB, and we have a chord named CD, and we have them intersecting at point X, again, we know that AX times XB, small piece times small piece of the red, has to equal small piece times small piece of the blue. Okay, that's our third theorem of the day. Now, in the proof of this example on page 343 that we're not really going to go through, the proof actually utilizes our final theorem of the day, and that's actually talking about some angles inside of this. Now, it's not actually a theorem about a chord like the lesson told us it is, but this is an important theorem to know for later on, and this is where the book talks about it. And what this theorem says is that if we have an angle inscribed on a circle, which you probably don't know what the word inscribed means yet, but it's when the angle is on the circle, and we have another inscribed angle on the circle that opens up onto this same arc. Notice both the red and the blue angle open up onto this same arc. Those two angles then on the circle are going to be congruent to each other because of this fact. Okay, and we'll definitely work more with that later, but this is where the book talks about it originally, is in this proof. Okay, so to kind of take some practice then finally with, again, the chord theorem. Again, we want small piece times small piece of one of our chords to equal small piece times small piece of the other. So x times x is going to equal 49 times 4. Well, x times x is x squared. 49 times 4 is 196. And if we square root that to find the measure of x, we end up with x equaling 14. Okay. Sometimes you're going to see, I know this example is not in your book, but you may want to write it down off to the side, ones that involve expressions. So notice it's not just x, it's x plus 1. So in this case, again, we're going to take small piece times small piece of one chord, so 4 times x plus 4, and we're going to set that equal to small piece times small piece of the other chord. Okay. So from here, what we're going to do is we're going to distribute, and that's why I put parentheses around our expression, because we need to remember to distribute, because we have 4 times x and 4 times 4, and then we have 6 times x and then 6 times 1. And now we're going to solve for x using these facts, right? We're going to draw in. I'm going to subtract the 4x from both sides. And I have 2x plus 6 on my right equals 16 on my left. And then I'm going to subtract the 6 so I can get my x all by its lonesome. 2x equals 10. And then finally, when I divide by 2, I get x equal to 5. Now, the question wants us to find the length, though, of TV, which is the red chord, right there. So part of that chord is 4. The other part is x, so 5 plus 4. So that's 9. So the total length is small piece plus small piece, which is 13. Okay. So to finish up today, okay, we have, again, 4 different chords, and this is, again, on the graphic organizer that you started yesterday. These are the last 2 slides, 3 and 4. And we want a couple examples to draw in. Okay, the first is when a diameter is perpendicular to a chord, it bisects the chord. So if you draw yourself a diameter and you draw yourself a chord, and we know they're perpendicular, we also know that this chord is cut into 2 equal pieces. Okay, so if we call this x, y, z, we know that x, y is congruent to y, z. Okay, and that's all because they're perpendicular. The next one then is talking about the chords being congruent, and then they are also equidistant. So if we draw in 2 chords that we know are congruent, okay, let's call them XY, and let's call the other one AB. Okay. If these 2 chords are congruent, then we know they're the same distance from the center. Okay, so if XY is congruent to AB, then we also know that these little pieces are also congruent. So let's call this Z and C. We know that then ZO is congruent to CO as well. Okay, this fact will hold true. The last chord theorem that we have here is, again, goes back to small piece times small piece. If we have these intersecting pieces, chords inside of a circle, if we name them A, B, C, and D, we know that our 2 small pieces, A times B, times B has to equal our other two small pieces, C times D. And lastly, again, this is not really to deal with our chord or anything with chords, but if we have these two angles that both open up onto the same arc, we know that the angles are congruent to each other. Okay, they're opening to that same arc. We'll talk more about why that's true in later lessons when we get to talking about angles and circles instead of just the chords. Okay. Thanks everyone for watching. Make sure you have this completely filled out, rewatch if necessary, and we'll work more with how to actually use these in class.